Bismillahirrahmanirrahim. This is linear system theory, homework 4. Question number 1. Schematic diagram is given. This is a scientific probe, gravity probe B, having this is the mass 1, this is the mass 2, this is the spring constant, this is the spring, and this is the passive damper. We are having the control force U, and this is the Y1 is the relative displacement y1 of the mass body m1, y2 is the displacement of m2 with respect to this position. The mass of m1 is equal to 2000 kg, the mass of m2 is 1000 kg, and the values of the k and v's are also given here. The part 1 is write the dynamic equation of motion for the consist of m1 m2 for the body m1 m2, position variable y1 and y2. Similarly, the actual disturbance u is a micrometer, right? The resulting motion is very small, therefore rewrite the equation with the scaled version. Z1 is given here, 10 to the power 6 y1, Z2 is 10 to the power 6 y2, and v is equal to 1000 times u, control force. Part C says that the equation is write the equation in the state variable form using the this is the state factor, and we're having the output factor y that is equal to z2, and this is the impulse force 10 to the power minus 3 delta. Similarly, by plugging in the numerical values into the equation of motion in MATLAB, having this is x dot that is ax plus bv, y equal to cx plus dv. So this is the system in the state space form. Part E says that use the MATLAB command P that is equal to calculate the poles that is equal to poles of the system matrix and the zeros of the state space matrices A, B, C, D. So this is the system is in the state space form. This is part 1. We are having the equation of motion that is the Newton's second law. So m1 that is F equal to ma. So this is the mass and this is the acceleration, m1 y1 double dot. So this is the spring for the relative the velocity between the 2 point y1 minus y2, and we are having the spring. So this is the relative displacement y1 minus y2. This is the control force minus u that equal to 0. So by simplifying, m1 y1 double dot is that is equal to this. Similarly, applying the equation of motion second law to the body m mass 2. So m2 y2 double dot that is equal to v y2 minus y1 plus k y2 minus 1 is equal to 0. There is no force here. So after simplification, we got this relationship. So these are equation 1 and 2, which will be further used in the part B and onward. So part B says that the actual disturbance u is a micrometer, right? So the resulting motion is very small. Therefore, rewrite equation with the scaled variables. So these are the scaled variables. We are having this equation y1 that is equal to z1 divided by 10 to the power 6. So we have to differentiate it. This is the twice. This is the first differentiation, and this is the second differentiation. Similarly, by differentiating y2 is y2 double and y2 dot, and similarly this is y2 double dot. So by plugging the values of the y1 dot, y2 dot, y1 double dot, and y2 double dot in equation 1 and 2, we got this relationship. So this is the final relation. M1 Z1 double dot. So now this equation is in the Z1 Z1 dot and Z2 dot and Z1 and Z2 and Z1 double dot. Similarly, we are having the equation number 2 that is in the this is the scaled version represented as the Z variable, right? So M2 Z2 double dot that is equal to V Z1 dot minus Z2 dot. The part C says that we are having the state vector is given. We are having the state vector x that is equal to z1 dot, z2 dot, that is the transpose. And the V, the force is also given, which is equal to 1000 times U. Y equal to Z2, and U is equal to the control force that is equal to 10 raised to the power minus 3. So this is the we are having this is the state vector, and this is x1 dot is equal to, which is equal to x2. Similarly, x2 is equal to z1 double dot by just putting the values from the equation 3 and 4. We can write the z2 z1 double dot here, and the value of the z2 not here. And similarly, x3 is equal to x4. This is the state vector, state variable. So now this is the standard state space form, which is x dot is equal to ax plus bu. So here this is the system matrix A, and we are having the state vector z1 dot, z2 and z2 dot, and this is the B matrix 0 10 minus 3 and 1, and this is the control variable, the input variable V, and this is the output. We have y equal to across the z2. So we can alternatively we can write the state space representation. You can write it the x dot that is equal to ax plus bv, and y equal to cx plus dv. Here in this case we are having the value of d, the feed forward matrix, that is equal to 0. Now part D says that write the equation in the Ax that is equal to x dot, that is the state space representation Ax plus bv, y equal to cx plus dv. And similarly, this is the system matrix A, this is the B, this is C and D, and this is state space representation of the system. This is SS stands for the state space, and this is the impulse response of the system in the time domain. So as the time goes to infinity, the response of the system goes to 0. So this is now that the E part says that find the eigenvalues, find the poles of the system matrix A, which are the eigenvalues, that is equal to, by the command is equal to P equal to EIG into system matrix A. And similarly, these are the zeros, these are the zeros which is used the in the state space in the time domain form. We are having ABCD matrices. So this is the value p equal to minus 3.4. These are the values of the poles. Poles position minus 3.45 plus 69.169. This is I omega. Poles of multiplicity. And here we are having these are the zeros, the position of the zeros. So now the zeros and fours are in the left half plane. Question number 2 says that so it means that the system is, which means the system is stable. Now question number 2 says the A matrix is given. Calculate a to power 80 using the transfer function. This is a matrix exponential by using the Jordan decomposition method and the transfer function method. So the transfer function method e to the power 80, that is equal to, by definition, that is the inverse of the Si minus A inverse. So initially first we will find Si minus A. This is Si minus A. And then by calculating Si minus A inverse, that is equal to adjoin Si minus A, the determinant Si minus A. So here in this part we are having a polynomial in the denominator. So we will we will simplify this denominator by using the partial fraction method, by putting s equal to minus 2 and similarly s equal to minus 1. So we got with the a is equal to 1 and b is equal to minus 1. So by applying the inverse Laplace transformation, we got these values e to the power minus t here, This is A1, this is the 1, and this one is here, this is a scalar, so this is e to power minus t, and these are all the values. Now to find the same, we are having the same matrix A by using the Jordan decomposition method. We are having the Ax that is equal to lambda x, so the lambda I minus is equal to x. So now we will calculate the determinant of lambda I minus A, which comes out to be minus 1 and minus 2. Similarly, now here to find the permutation matrix or the P matrix, we need to find the the eigenvectors x here, x1 and x2. So by putting lambda 1 that is equal to minus 1 here, so we need to satisfy this equation. So that is equal to x1, x2. Here x1 is equal to 1 and x2 here is 0, x and x1 is free variable. So we satisfy this equation. Similarly, lambda, by plugging in the value of the lambda 2, x1 and x2 is that is it comes out to be x1 that is equal to minus x1 minus x2 comes out to 0 by taking the negative common, so it comes up to be x2 is equal to x1. Now by putting arbitrarily that x1 equal to 1, x2 comes out to be minus 1. So this is the P matrix. Similarly, this is the inverse of the P matrix. And by definition, the A matrix that is equal to P times e to the power big lambda, and this is P inverse. So by plugging in all the values, we got the same result. So thank you.